Okay, 11.2 take 2 here. So 11.2 is all about hypothesis testing two population means when we don't know our standard deviation, mirroring that of chapter 10. So we'll be looking at a t-score for this. We have two objectives. These are basically the same objectives that we have this whole chapter. To go over the test statistic and rejection region. I forgot to write rejection. And then to perform the hypothesis test. So, as I said, our test statistic, when we don't know our standard deviation, is a t-score. Now, you'll remember that we have two different test statistics for two different occurrences. The first is when we have unequal variances in our samples. So for two samples that they have to be at least 30 or approximately normal so we can use the student distribution. Our test statistic t for unequal variances is x bar 1 minus x bar 2, bar got a little high there, minus parentheses mu1 minus mu2, all over big square root here, s1 squared over n1 plus s2 squared over n2. And this mu1, so x bar 1, s1, n1, and n1 are the sample mean, standard deviation, and size of the sample population 1. X bar 2, s2, n2, sample mean, standard deviation, and size of population 2. It doesn't actually matter which population you label as 1 or 2. Just make sure you're consistent. Then the degrees of freedom that you use is the smaller of either n1 minus 1 or n2 minus 1. So you look at both and then you pick your smaller one. Your mu1 minus mu2, this is always going to end up coming from our null hypothesis as usual. So coming down, taking a look at what our hypotheses may be will tell us what this value is. So we have our three types of tests, left-tailed, right-tailed, and two-tailed. So the left-tailed is always going to be our null is m1 minus m2 is greater than or equal to a. So that's where this value comes from. Whatever this number a is, that's what gets put here. As we've talked about in the last section, many times this a is going to end up being a 0 because that's the most common thing, but not always. We're going to do an example or two throughout the chapter, well, more than two. We're going to do examples that have non-zero a values. Our right-tailed test, mu1 minus mu2, is less than or equal to a is our null hypothesis, and then greater than a for our alternative. And then two-tailed, of course, is the equal and not equal version. So let's continue on here and talk about the rejection regions before we jump into some examples. So we reject our null hypothesis if one of the following occurs. If our t-value is less than or equal to negative t sub alpha, this is for a left-tailed test. If t is greater than or equal to positive t sub alpha, this is for the right-tailed test. And then if the absolute value of t is greater than or equal to t sub alpha over 2, this is, of course, for the two-tailed test. So let's take a look at an example, go all the way through start to finish. So suppose that the Smith CPA firm claims that its clients receive larger tax refunds on average than the clients of its competitor, Jones and Company CPA. Really creative names, I know. To test this claim, 15 clients from the Smith firm are randomly selected and found to have a mean tax refund of $942, and I am forever jealous. I would love a refund that size. This is with a standard deviation of $103. At the Jones firm, a random sample of 18 clients are surveyed, and they find that they get a mean refund of $898. Again, I wish I got that. And the standard deviation for that sampling is $95. We're going to test the claim made by the Smith firm using a level of significance of 0.05. And because we don't hit those number requirements on our sample sizes, we're going to assume populations are both normally distributed. Okay, so hypothesis testing starts the same as always. Identify your hypotheses, our null and our alternative. So the null hypothesis Goes back to the first sentence. They claim that their clients receive a larger tax refund. So you can see this in two ways. Either their claim, mu1 minus mu2, is bigger than 0, or the alternative, mu1 minus mu2, is less than or equal to 0. So let's talk a little bit about how we would come to this conclusion for the 0. Because all the problem tells us is that they think they get a higher average refund. That's what they think. That's always going to be the alternative. Which means that if you took their company and you subtracted away the other company's average, theirs would be greater than 0. If they were the same, which would fail their claim, it'd be equal to 0. And if they're worse off, then when we subtract it, it'd be less than 0. So that's how we get to this conclusion with these hypotheses. And so next we want to just label all of our pieces of information. Now I am working under the assumption that the Smith company is the population or sample 1, and then the Jones company will be population or sample 2. So that means that X bar 1 is 942, with S1 being 103, and N1 being 15. X bar 2 then is 898, with S2 being 95, and N2 being 18. Our alpha value is 0.05, and our degrees of freedom for our test statistic, 15 minus 1 is going to be smaller than 18 minus 1, so that's going to be 14. So, obviously we could punch into our formula, calculate T, look up the critical T-score. So I'm going to go through how to do this in the calculator though, because everything else is stuff that we've done. The hard part about this is getting it set up. So for the calculator portion, if you're doing this by calculator, you go to Stat, over to Tests, and you're looking for the 2-samp t-test. I forget which option it is, but this is what we're looking for, 2-samp t-test. You want to make sure that you have stats selected, and then enter our info. You'll see there are spots for each of these 6 things here. So enter our values. Make sure that you select the correct tailed test. So we are doing a right tailed test, so we pick the greater than mu2. Again, and you can think of this as rewriting this alternative hypothesis as mu1 is greater than mu2. Make sure that there's an option for pooled, and make sure that is no. We're not pooling any data. And then hit calculate. So once you hit calculate, you should see the screen. And it has a bunch of information, all things that we can use. And let's see, I might as well just show you while you're doing this. I already have it run. Here we go. So a couple things. You can make sure that you have the right test. We are right tail mu1 greater than mu2. We have our t-score, we have our p-value. We'll come back to the degrees of freedom. Our x bar 1, x bar 2, sx1, sx2, n1, n2, all of those are just repeated. Now, the thing about the degrees of freedom, this is not the degrees of freedom that we would have used to calculate t sub alpha. This is a different degree of freedom associated with this particular t-score. So there's usually some confusion about that. Remember that this number here is if you're looking to find t sub alpha, t sub 0.05. This degrees of freedom score or number is different. It's associated with our t-score that we've just found. So speaking of our t-score, our t-value is 1.266 approximately. Since this is a right-tailed test, we look at this compared to t sub alpha. T sub alpha, this is where we use our degrees of freedom, and you can do that using the inverse t or looking up in the t tables, but we get 1.761 for our t sub alpha, and 1.266 is less than 1.761. So looking at our rejection regions, We are not greater than or equal to T sub alpha, so we're going to fail to reject our null hypothesis. And that means that there is not sufficient evidence the Smith firm has a higher average, running out of space here, return or refund. Okay, so let's go through another example now to use the steps. But for this one, we're going to shift gears, and as we mentioned, that was the unequal variances. Now we're going to look at what happens when we have equal variances. And if you remember from chapter 10, the equal variance variety is always more complicated. So again, 2 samples, at least 30 in sample size or approximately normally distributed. Our test statistic T, in this case, it's a real big fraction, so give yourself lots of space. The top is x bar 1 minus x bar 2 minus mu sub 1 minus mu sub 2. The bottom, however, is a very large square root, and it is n1 minus 1, so it's n1 minus 1 times s1 squared plus n2 minus 1 times s2 squared all over n1 plus n2 minus 2 times the quantity 1 over n2 plus 1 over n1. Now, a lot of times you'll see this formula split with 2 radicals. It doesn't need to be split into 2 radicals, but you can. So if you're following along in the book, you'll see that there is a second radical here, and they split this. It's the same thing. We can combine radicals with multiplication. Again, all of the variables mean the same thing. The big difference now is our degrees of freedom changes. So it's no longer the smaller of n1 minus 1 or n2 minus 1. The degrees of freedom for a equal varianced double sample is n1 plus n2 minus 2. So in effect, you add up the 2 options and use that. Okay, so this is a nice big block of text here. A home improvement warehouse claims that people interested in completing their own projects can save time, their own home improvement projects can save time by attending workshops. The warehouse claims that people who attend its tiling workshops, for example, will take less time, on average, to complete a tiling project than those who don't attend one. To test this, a randomly selected group of 10 people who attended the workshops are surveyed. They spent an average time of 14.1 hours with a standard deviation of 2.3 hours. Another randomly selected 10 people who did not attend any workshops took an average time of 15 hours to complete their tiling projects with a standard deviation of 2.4 hours. We're going to test this warehouse's claim using significance level of 0.01, assuming again, since our sample sizes are too small, that both populations are normally distributed. So first things first, I should use the right color. Get our hypotheses, null and alternatives. So again, mu1 minus mu2 and mu1 minus mu2, this is how our always look. So the warehouse is claiming that the average time of people who take their workshops will be less than the others. So if we think of the first population as those who took the workshops, then when we do mu1 minus mu2, this should be less than 0 for the alternative. And the null hypothesis, don't know what happened to my mouth there, would be greater than or equal to 0. And that's because this should be smaller. So if this is smaller, when you subtract, you should get a negative. If they're the same, then their claim is wrong, and that would mean that their average times when we subtract is 0. And if they are longer, or people take longer if they take the workshops, it'd be greater than 0. So these are our null alternative, X bar 1 is going to be, population 1 is going to be the people who took the workshop. So the average is 14.1, standard deviation 2.3, and sample size of 10. X bar 2 is 15 then. These are people who did not take the workshop. S2 is 2.4, and N2 equals 10. Our degrees of freedom for alpha being 0.01 is N1 plus N2 minus 2, so that's 18. So we're going to use the calculator again. You can, of course, plug in all your numbers here and get your T, and then compare that to the critical T score. So we're doing the 2-sample t-test again. We're going to enter in all of our information. Make sure that we are picking the correct tailed test now. We're doing a left-tailed test. And make sure that you don't have pooled on because we're still not pooling any data. And hit calculate. And we should get that t is approximately negative 0.856, rounding off to 3 decimals. Our p-value is 0.201. And so we're going to use the p-values in this case. Our p-value of 0.201, this is greater than our alpha 0.01. Since this is a left-tailed test, that means that we are not in the tail, and so we fail to reject the null hypothesis. And ultimately, that means that there is not sufficient evidence I can spell that word, that workshoppers finish their project or projects any faster, on average. And I'm out of space, so I'm going to abbreviate as AVG. It doesn't mean that they don't. Some people may finish faster if they go to the workshop. Some people don't. Maybe you just have naturally gifted. Also, there's a big flaw in this in that we don't account for professionals or semi-professionals or people who have a lot of experience. So that's what we get. Okay, so there's 11.2. I'll be working on 11.3 shortly here to get that up as well.